В чем проблема? Там видим это что?
Переключать слайд.
А там что, не на компьютере?
Нет, там можно просто сидеть, чтобы он писал.
Technical issue. No, it's okay.
Презентатор.
Так что?
Ну, презентацию.
Было на самом деле поставить это сюда, просто а может быть там, вы поможете там? Probably we begin right now because Evgeny will help you. You just say next slide, and, no problem. May I say a few words at the very beginning, dear friends, dear colleagues. I'm very glad to introduce to you a very well-known mathematician and rector of Primorska University from Koper, Slovenian town, not far from Portorož, from Trieste in Italy, and we are happy to have here our guests from that university and people from business community of Slovenia who participated yesterday at the conference we organized together here. And now Professor is going to present a lecture in the field of mathematical science, which is his specialization. So we are happy to greet you here, and please, you're welcome.
Thank you. First of all, thank you for giving me this opportunity. Здравствуйте. Povej da sam povešiti malo v ruščini, da sem izredno vesel, da sem tukaj.
Povem zdaj?
Ja, povej.
Я по-быстрому вас только на русском еще поприветствую. Значит, профессор Марушич очень рад, что он сегодня с вами. Естественно, преподавать будет на английском языке, но если что-то будет непонятно, то уже переведем. Здравствуйте.
Again, I'm really very honored to be able to give a lecture at your university. Let me first explain just a couple of sentences where my background comes from. I got my first degree at the University of Ljubljana in the old days of Yugoslavia, and then in the late 70s I went to England. I was one of the first students who decided to perhaps pursue a PhD outside my home country. I got my PhD from Reading University in England, and my supervisor was Professor Nash Williams, now deceased. He was a set theorist and a graph theorist. My love for mathematics sort of comes from algebra and group theory, and the main topic of my research has been sort of a mixture of discrete mathematics and graph theory networks, but looking for symmetry of these objects, and therefore using permutation groups and abstract groups as well. So the purpose of this talk is to explain what has been going on over the last few decades in two open problems in this area. One concerns so-called Hamiltonian cycles and paths in vertex-transitive graphs. I will explain all of this terminology. And the other one, existence of so-called semi-regular automorphisms in such graphs. As I have my colleagues who are here with me, who are not mathematicians, and my thesis is that a lot of these problems, still open problems in graph theory, are easy to explain, easy to understand, but very difficult to prove. And I will try to give this lecture in such a way that it is understandable to as large an audience as possible for as long as possible. But at some point, things will become a little bit more complicated. This is the picture of Koper. It happens to be my hometown as well, and also the place where, or the seat of the third university in size and chronological existence. There are two other universities, the oldest one in Ljubljana, the capital of Slovenia, and the second one in Maribor, up in the northeastern part of Slovenia. And this is the central square in Koper. Just opposite the church is the rectorate of the university. Okay, I come from, originally from the Faculty of Mathematics, Natural Sciences and Information Technology. The university came to existence in 2003, sort of at about the same time as the Moscow School of Economics. The Faculty of Mathematics, maybe 4 years later, 2007. And this is a young and vibrant faculty with a lot of international cooperation from universities and scholars from all, essentially from all continents. We also publish a mathematical journal, Science Citation. It's in the Science Citation base, Ars Mathematica Contemporanea. Okay, the two important problems in vertex transitive graphs. One concerns existence of Hamiltonian paths and cycles, and the other one existence of so-called semi-regular automorphisms. Here, I'm going to explain now what this terminology means. A graph is just a collection of a pair of two objects, two sets. The first set, elements of the first set are usually called vertices. So they're just a collection, a pair of two sets. So V is set, non-empty. Elements are called vertices, and E is just a relation. Usually, essentially, we can assume for the purpose of this talk that the relation is symmetric and irreflexive. Just explaining this, I know that most of you know, but for my colleagues, so just think of V as people and E as friends. Okay, this is a being friends or knowing each other is a relation which is symmetric. We're assuming that if A knows B, B knows A, and of course when we say reflexive, we disregard the obvious fact that somebody knows himself or herself. But as psychologists say, no, you can live a whole life and without really coming to terms with your own personality. So a perfect example is people and friendship, but we have a lot of other models such as telecommunication systems or computers or web. The World Wide Web is another example. Lots of different examples.
Nobody is a friend of herself. Yeah.
Yes.
Which means irreflective.
I think that would be a way to look at it. Okay, so usually the way we do this is we use pictures, which is why we use the term graph. It is not a graph of a function. suppose we have V, I don't know, 1, 2, 3, 3 elements, and E consists of 1 and 2 and 2 and 3. I'm just simplifying this. If you think of this as a two element set, then the picture would be something like this. Just draw a line, a connection line between two elements if they are in relation. Okay, so that would be it. Now, so this is a graph. And what is a vertex transitive graph? As in other areas of mathematics, we use mappings, which are sort of consistent with the inner structure of these objects, to help us understand what are the symmetric notions of these objects. For example, in this particular case, if we take the permutation of the set 1, 2, 3, which leaves 2 as it is, so we fix 2, but we interchange 1 and 3. So then the picture will be, so when we do this transformation, then the picture will be this. So this becomes 3, this becomes 1. Now, nothing has changed. We have just relabeled the vertices, but 2 and 3 are still, we say, adjacent, or are still in relation, and 1 and 2 are still in relation. So such permutations are called automorphisms. So the permutation, I call it alpha, which leaves 2 unchanged and interchanges 1 and 3, this permutation is called an automorphism because it leaves the adjacency of vertices unchanged. Out of all permutations, those special ones are called automorphisms. Okay, so we now know what an automorphism is. So it is a permutation that leaves the structure unobstructed. A graph is vertex transitive if we can, for any pair of vertices, we can find one automorphism which takes one vertex to the other. Now, this is not vertex transitive because we can never take 1 to 2 or 3 to 2. We can only interchange 1 and 3. So 2 is a special vertex here because it has, if you look at it, it has 2 neighbors or 2 friends, whereas 1 and 3, they only are friends with 2. So this graph is not vertex transitive. Vertex transitive are those graphs which have this homogeneity property. Okay, so that's vertex transitive. What is a Hamiltonian parallel cycle? This is much easier to explain. Think of you as taking a walk through the graph. You go from, a walk would be, you go from one vertex to another, but you have to choose a path. So choose this adjacency pair. You go from one vertex to another. If there are friends, you go from one person to another. You're visiting, you come to another person, but you have to go through friends, mutual friends. Okay? So if you can walk through the graph in such a way that you starting at one vertex and you travel through all other vertices, but going through each vertex only once you get in, you have to go out, then this is called a Hamiltonian path. For example, a Hamiltonian path in this graph would be, let's just go like this. So you travel through all the vertices, and you've only been to any vertex just once. If you start at a tip and end at 2 different vertices, then this is called a path. If, for some reason, you happen to come back to the same vertex, so you do a cycle, then this is called a Hamiltonian cycle. So a Hamiltonicity, Hamiltonian comes from a British mathematician in the 19th century who studied its properties. Hamiltonian means going through all the vertices, but traveling through each vertex just once. Okay, so that's Hamiltonian. and I will explain semi-regular automorphisms later in my last part of my lecture, because I'd like to move to this problem of Hamiltonian properties. So I will first give you more formal definitions, and then I will talk about Hamiltonicity. Okay, so I just explained before. So vertex transitivity means for any pair of vertices, you find a permutation that leaves the adjacencies alone, unchanged, and you are able to map one vertex to the other. So that means vertex transitive you can do for an arbitrary pair of vertices. Just as another example, if you look at these two pictures, the one on the right hand side is vertex transitive, and the other one is not. Now, this example, I was sort of cheating because it is obvious that you cannot map 1 to 2, because 1 only has one friend and 2 has two friends. So you cannot, when you map two vertices or two persons, can only be mapped one to another if their local properties, at least local properties, have to be the same. But in these two examples, you will see that every vertex has 4 neighbors, every 4 friends. So it is, at least potentially, it would be possible to map every vertex to every other vertex. Now, the picture on the right-hand side, there is sort of an obvious way to do this. You just rotate the picture clockwise or counterclockwise, doesn't matter. You go from one vertex to the neighboring, and you do it seven times. So you can really get from every vertex to every other to any other vertex. Is this sort of understandable? You should not be misled by the picture is not sort of geometric. It's not equilateral. But what matters is that are connections between vertices. And so as far as connections are concerned, if you take, for example, the top vertex, you can move it to the right-hand side vertex, and then the whole picture sort of turns by 1/7 of the full angle. Now, why? If you look at the left-hand side picture, every vertex has 4 friends, but why is it that you cannot map every vertex to every other vertex? The easiest way to understand this or to see this is by looking at non-friends. So for every vertex, look at those vertices which are not adjacent to that vertex. So each vertex has 2 non-friends. Now there is an obvious triangle of non-friends. If you look at the top vertex, I'm looking at the left-hand side picture, top vertex, it is not adjacent to 2 vertices, one to the right, one to the left, and those 2 are also not adjacent to each other. So there is a non-triangle, if I may say so. On the other hand, the sort of the bottom 4 vertices, look at the bottom 4 vertices, the vertex which is on top of the wording is not vertex transitive, is not adjacent to the left and the right vertex, and if you look at these 4 vertices, they give you a non-quadrangle. So the complement of this graph is a union of a triangle and a quadrangle. And there is, of course, when you're looking for permutations which preserve friendship, they also preserve non-friendship. That is an obvious way to look at permutations and automorphisms. Preserving adjacency or friendship is equivalent to preserving non-adjacency, non-friendship. So it is not possible to find enough automorphisms to make the left-hand side picture vertex transitive, because the complement of this graph is a union of a triangle and a quadrangle. So we have homogeneous sort of graphs which are not vertex transitive. The easiest, an obvious way to construct vertex transitive graphs is using groups. Such graphs are called Cayley graphs. This is a historic reason, but there is no obvious connection as to why they would have to be called Cayley, because Cayley goes by Arthur Cayley, but in historic books I have never found a good reason as to why such graphs are called Cayley graphs, because I don't think he has done anything on it, but for some reason this is what they are called. So if you have a group, so you have the explanation there. I will just give you an example, okay? Suppose that group is cyclic group of order 7. And we have the obvious addition modulo 7. And suppose we take the set S to be 1, 6, 2, 5. It has to be symmetric. Symmetric in this sense means it has to be S equals minus S. And what I do here is, okay, the wording there is using multiplication, but I'm going to change that multiplication with addition. So what would be the graph in this case? For example, what are the friends of 1? I'm changing multiplication to addition. So 1 is adjacent to 1 plus 1, because G goes to GS. So 1, the neighbors are of 1. One plus 1 equals 2. 1 plus 6 equals 0. 1 plus 2 equals 3, and 1 plus 5 equals 6. These are my neighbors. And if you sort of repeat this for 2, 3, and so on, this is what you would get. You actually get the graph that we had before, right? So this is just, this picture here is a picture of a graph, of a Cayley graph of cyclic group of order 7 with respect to this set, which is usually called the symbol of the graph. Okay, now why is this vertex transitive? Because there is an obvious way to go from one vertex to another. Namely, every element of the group gives you a permutation, which is an automorphism. Every element of Z7 can be used as a permutation that preserves adjacency. You just rotate the picture 7 times and you get it. And the beauty of this is that this works for every group, just as is mentioned there. Okay, so now we know what a vertex transitive graph is. We know that there is a family of graphs which can be obtained from groups, and they are vertex transitive, but not all vertex transitive graphs are obtained in such a way. And the smallest one is a graph that I would like to mention this takes part in this lecture. It is there. So I explained Hamiltonian cycles and paths and explained what a vertex transitive graph is. There is an obvious way to construct vertex transitivity through direct approach, with a direct approach.
This is not a general method of construction.
No, this is not a general. There's a more general.
No.
There is a more general where you use a group and a subgroup, and you work with cosets of that subgroup. But perhaps later on, maybe it's not essential for this lecture, so I would just like to leave it out for the moment. So here is the central question that I would like to discuss. Is it true that every connected vertex transitive graph admits such a Hamiltonian path? Connected just means that it is made of one piece. Okay, so if you just look at this friendship, every person can go through traveling through friends can get to any other person. So that's what connected means. The question was posed in 1969, appeared in a book, proceeding of a conference in Canada in 1970. But it is the author, or sort of the first one who posed this question was Laszlo Lovas, a Hungarian mathematician, graph theorist. And as I said, late 60s, 1970 was the first time it appeared in writing. Now, a lot of work has been done, but the question is far from being completed. Now, there are examples to make the whole thing even more complicated. A path is, you start at a vertex, you end at a different vertex. A cycle, you end at the same vertex. Now, not only, so the question only asks for a path, not for a cycle. But the complication is, or the mystery is that we only know of 5 graphs, or essentially 4 graphs, which are vertex transitive and do not have a cycle. So all other graphs that we know, they do actually have a cycle, except for these 4 special examples, of which essentially there are only 2 really, 2 examples that should be considered as counter-examples to possible existence of cycles. There are 2 other that are obtained from these graphs, and there is one obvious, of course, if you just take one edge, 2 vertices with one edge. This graph is vertex transitive, but there is no way to have a cycle because it just doesn't have enough space to produce a cycle. So essentially we would be cheating if we consider this as a counterexample, but okay, this is a vertex transitive graph. It has a path from one vertex to another, but it cannot have a cycle. But I would like to draw the Peterson graph, the smallest graph, which I believe is a good example to study this. A lot of properties in symmetry of graphs. There is a 5 cycle on the outside and a star on the inside, and the connection from the outside cycle to the inner star. Now, this graph is vertex transitive. It is not a Cayley graph, and it doesn't have a Hamiltonian cycle, but it has a Hamiltonian path. Now, that it has a Hamiltonian path is sort of obvious. You just sort of travel like this on the outer cycle, you get to the inner cycle, and then you complete it. But of course, you come back to the wrong vertex. There's no way to get out of this inner star and come back to the outer rim. Okay, so this does have a Hamiltonian path. Now, why is it that it is vertex transitive? Now, there is an obvious symmetry of order 5. So every vertex on the outside can be moved to any other vertex on the outside. And while we are doing this, we are also moving the inside 5 star. I think this is sort of obvious from the picture. But why is it that I'm sort of pressing this? Why is it that we can go from every outside vertex to every inside and vice versa? I'm going to cheat now. There is a nice way of drawing this graph, which sort of shows you that what we have behind is the symmetric group on 5 letters. So I'm going to draw. I'm going to label the vertices, and if you want, you can do it on your own as well. I'm going to label these vertices with pairs of elements from the set with 5 elements. There are precisely 10 pairs, 10 two subsets, and the problem is, try to do this in such a way that every vertex gets a label, a pair of 2 elements from this set, in such a way that 2 neighbors have empty intersection. If I do 1, 2 here, the 3 other neighbors will have to receive 3, 4, 3, 5, and 4, 5. So I'm going to do 3, 4 for this one, 4, 5 here, and 3, 5 there. So I have labeled these 4 vertices in such a way that when I look at 2 neighbors, they have empty intersection. If I think of this as a subset with 2 elements, okay? Now, so here's for this 3, 5 vertex. These 2 vertices have to be 1, 4 and 2, 4, and I believe I can sort of, it doesn't matter which way I go. It turns out that it doesn't matter. So I'm going to do 1, 4 here and 2, 4 there. Now I am already restricted by already having these 2 neighbors labeled, and there is not much I can do here. There is, I'm forced to use 1, 5, okay? This has to be 1, 5. There is only one left for this vertex, 3, 4, 2, 4, 2, 3. And the rest is forced as well. So if you check all the connections, any edge, any adjacency is has the 2 vertices labeled by a pair, by 2 pairs which have empty intersection. Okay. Yeah.
There should be a connection between 1, 5 and 1, 2, because 1, 2 is the front of the front of 1, 5. Yeah. 1, 2 is the front of 1, 5, and the front of my friend should be my friend. There is no connection between 1, 5 and 1, 2.
No, but it cannot be, because 1, 5 and 1, 2 have an empty, non-empty intersection. So the rule is I'm joining UV with X, Y, if and only if UV has empty intersection with X, Y. This is the rule of adjacency. So 2 pairs are adjacent if and only if the corresponding 2 subsets have empty intersection.
Probably I do not understand the definition of the transitivity. I understand it as the friend of my friend is my friend. Is it correct?
No. Vertex. No, this is not transitivity of the relation. Transitivity, vertex transitivity, just means that for any 2 vertices, there exists a permutation which is an automorphism, such that alpha takes U to V. It's confusing. Yeah. Transitivity is not the transitivity of a relation, the transitivity of the action of the permutation groups, group. But is that okay with you? This is the okay. The graph, as I said before, I gave you the graph before the label. Now, the thing is that I can label the vertices in such a way that I follow this criterion, if you want. If I follow this rule, for 2 vertices labeled UV and XY will be joined or will be adjacent if and only if the corresponding u, v, and x, y subsets have empty intersection. And I can do this precisely. I can do this for this picture. Is that okay? Now, the beauty of this labeling is that it gives you you just have to do one step further and see that every permutation of this set gives you an automorphism, induces an automorphism, because I can now do the following. I can say, well, I'm going to take a permutation of this set, for example, a permutation that a transposition that interchanges 1 and 2, and I'm going to leave 3, 4, and 5 unchanged as a permutation of this set. Now I'm going to use this permutation to produce an automorphism of this graph. And I will do this, I'm going to use a red labeling. So 1, 2 will stay 1, 2, because I have only interchanged 1 with 2, but this 2 subset not changed. Okay, so this stays where it was. How about 3, 5? 3, 5 stays where it is. 4, 5 also, and 3, 4 also. So I have essentially these 4 vertices they have not changed, because such is the permutation. I'm only going to change 1 and 2. So if I'm changing 1 and 2, I have to, this becomes 2, 4, and this becomes 1, 4. Yeah? These two are interchanged. This and these two. This becomes 2, 5, this becomes 1, 2. So I'm leaving these 4 vertices. I'm changing these two. I'm changing these two, those two, and those two. So as a permutation of this 10 element set, I'm leaving fixed 4 points, 4 vertices, and the other 6 are sort of moved in pairs. 3 pairs of 2. 3 pairs. Yeah. Now, as you see, while doing this, I have not changed the adjacencies, because before, after the relabeling, everything looks the same as before. What has this outside rim become? Okay, running out of colors, but let me draw this 5 cycle, black 5 cycle. I'm going to draw it with red color. But these 2 edges are left as they were. But 2, 4 has moved into 1, 4. So this edge has moved to that edge. This edge, just a second, these two go, this edge goes to that edge. And 1, 5, and 3, 4 becomes this one. So the outside 5 cycle has become this red 5 cycle. And the other, the other 5 vertices will also give you, so the inner star has become this 5 cycle. And the other 5 the other 5 in between edges sort of also move in the right way. So essentially what I'm saying is that every permutation of S5 will give you an automorphism of this graph. And this is a way to prove that the number of automorphisms of this graph is precisely 120, and the automorphism group is isomorphic to S5. It also shows you that I really can move a vertex on the outside to a vertex on the inside. So I have essentially shown you that this is a vertex transitive graph. Now, why is it that this graph is not Ka? There are only 2 non-isomorphic groups on 10 elements, the cyclic group and the dihedral group. If you take a cyclic group, and you want to have 10 edges outside this in the Cayley graph, because the cyclic group is abelian, you can easily see that you will always have a cycle of length 4 in the graph. This is true for every abelian group, and it is also true for essentially for every dihedral group, with some exceptions, but which do not sort of come to existence in this particular case. So using the fact, I don't want to go in details, using the fact that there are only 2 non-isomorphic groups on 10 elements, abelian group Z10, which will always produce you a 4 cycle in a graph, and a dihedral group which will also produce you either a 4 cycle or will have some other properties that are not consistent with this graph. This is an argument that this is not a Cayley graph. Okay? And now, because we are doing Hamiltonian cycle, I'd just like to show you how am I doing time-wise. I'm definitely not going to go through all the material, but I'd like to be very as understandable as possible. How am I doing as far as time goes? How much more time have I got? 20 minutes or 15 minutes? Yeah. Okay, so how do we prove that this graph is not Hamiltonian? What would be our argument here? There are different ways of looking at this, but perhaps one of the easiest would be if I just start from the opposite assumption. Suppose that I can redraw this graph in such a way that I have a Hamiltonian cycle. In other words, suppose I can place these 10 vertices on a circle, if you want. And if this was the case, then it would be possible for me to draw 5 chords inside this cycle in such a way that this picture would be consistent with that picture. In other words, with a redrawing using an automorphism, I would be able to go from this picture to that picture. Now, there are many ways to look at this, but perhaps the easiest would be this. Suppose I take this vertex as my initial vertex. I can never draw a chord from this vertex to that vertex because this would give me a triangle. There are no triangles here. There is no sequence of 3 mutual friends, if you want. There is also no sequence of 4, no 4 cycle. The smallest cycle has length 5. So this guy here is either adjacent to this, that, or that. So suppose that every vertex, the chord from every vertex would go directly opposite to the directly opposite vertex. If I do this for every vertex, then I have a cycle of length 4. So this is not possible. So in other words, there has to be one vertex which is not joined to the opposite vertex. Okay, so let me assume that this is the vertex that is not joined to the directly opposite vertex. So if that vertex, the black vertex here is not joined to this one, it is either joined to this one or that one. It's either left or right. But it doesn't matter which one, because if it is, I can assume it is joined to this one, because if it was joined to that one, I would just go behind the blackboard and would look from the other position. So I can assume that this vertex here is joined to that. Okay? Now, how about this one? This one can either go here, or here, or here. At one of these 3. There's no other possibility. Because all other possibilities, this would be a triangle, this would be a 4 cycle, that would be a triangle, a 4 cycle. So these are the only 3 possibilities for that vertex as well. Either directly opposite or the other 2. But of course directly opposite is not possible because this vertex here is joined to that vertex.
So I can only go to this vertex or that vertex. But in both cases, I have a 4 cycle. A 4 cycle, and here I also have a 4 cycle. Okay, so this is a rather simple argument as to why this cannot be redrawn in this way. So this graph is called the Peterson graph. It is a counterexample or an example of many different properties in graph theory. For example, this is also called a snark. A snark is a graph which has every vertex has 3 neighbors. It has some other properties that are necessary, but essentially is that you cannot use only 3 colors to draw vertices. To draw edges of this graph in such a way that from every vertex, every edge on each vertex has 3 different colors. So you don't have a vertex with 2 edges of the same color meeting at one vertex. You cannot do this with 3 colors. You have to use 4 colors for that. And such graphs are called snarks. And this is the smallest example of a snark as well. Okay, so I hope that you got something out of it, because now I'm just going to give you an essential idea as to what is the situation as opposed to with regard to this problem. And the Peterson graph is this. The Coxeter graph has 28 vertices. Is a similar example of a graph which doesn't have a Hamiltonian cycle, but it has a Hamiltonian path. So the one on the left-hand side, the Peterson, the one on the right-hand side has 28 vertices. That is the picture. It comes from a projective linear group 2,7, and in this case, to prove that it doesn't have a Hamiltonian cycle is much more complicated, and I just don't have enough time. In fact, there was one paper written on it back in the 60s. So these are 2, and there is an obvious way to use these 2 to produce 2 other vertex transitive graphs which don't have a Hamiltonian cycle. And you do this by replacing each vertex with a triangle. And here is what you do. So this is the Peterson graph, where I have done the following. I have taken a neighborhood of one vertex, and I have replaced it with a triangle by placing a triangle in the position where before I had a vertex. So by doing so, I have gotten a graph on 30 vertices. And what is the argument for non-Hamiltonicity of this graph? Now, assume that I can find a Hamiltonian cycle in this graph, and then place yourself in an arbitrary vertex. This arbitrary vertex is a vertex on a triangle of what before was a vertex. Now, once you are there, in order to go through all the vertices of the graph, once you are in a triangle, once you hit one vertex of any of these 10 triangles, once you get to that vertex, you have to go to 2 other vertices, because there is no way of coming back. If I have gotten to this vertex, I either have to go like this and out, or like this and out. If I just do this and leave out this vertex, there is no way I can come back to this vertex and take care of this, because remember, I have to go to a vertex and out of that vertex. So I have to use 2 edges of that vertex. So a Hamiltonian cycle of this graph of 30 vertices has to have 2 vertices of each triangle. But if it has to have 2 vertices of each triangle, it essentially moves through triangles and completes 2 vertices of each triangle. You can project this so-called cycle to a cycle. You would be able to project this cycle to a cycle in the original graph, the Peterson graph. But the original graph does not have a cycle, so this one doesn't have a cycle. This is the argument as to why this graph doesn't have a Hamiltonian cycle. And you repeat the same thing with the Coxeter graph. So you get another one there. Of course, you can repeat this, you can do this ad infinitum, you continue doing this, but the problem is that you lose vertex transitivity. Only at the first step, the graph remains vertex transitive. When you go further, you lose vertex transitivity, you get graphs which are, of course, non-Hamiltonian, but they are not vertex transitive anymore. Okay, now there are several techniques used in proving that certain families of graphs have a Hamiltonian cycle. When this can be done when graphs are of particular number of vertices, doing with prime numbers, we can even do, but it is not written here, we can essentially do all vertex transitive graphs which have order of number of vertices, a product of two prime numbers. We can do Cayley graphs, so this was done by David Witt in the late 80s. Every Cayley graph of a P group, so take an arbitrary P group, an arbitrary Cayley graph of a P group, there is a Hamiltonian cycle. Other cases too, but what I would like to show you and finish off this talk without moving on to semi-regular automorphisms, because it is just too long. I would like to give you a few pictures and explain the latest theorem that we were able to prove before I became rector, because I don't have much time to do mathematics, and I'm so grateful for the opportunity to actually spend some time here thinking about mathematics. The problem or the theorem that we were able to prove for the particular case of graphs with cubic graphs are those graphs which have every vertex has 3 neighbors, because the idea is that what is the worst possible scenario of a vertex transitive graph without a Hamiltonian cycle or path, when you don't have a lot of neighbors, when you don't have a lot of ways to go from one vertex to another. And the smallest graphs in that respect are graphs where every vertex has just 3 neighbors. So that it would be line number 4. Cubic Cayley graphs with each vertex has 3 neighbors, where the connection set S consists of one generator of a group of order n, say, and one involution. So that is what I would like to finish off this lecture with. So if you have a Cayley graph with valency 3, a cubic Cayley graph, what are the possibilities? Now either, of course, if you want to have a connected Cayley graph of valency 3, cubic, there are 2 ways of doing this. Either you take 3 involutions. A group can be generated by 3 involutions. This is the first line there. A, B, C are the 3 involutions. And and the second case is where you have one involution A and one element X of order S. I think it is there, S, where S is at least 3. So these are 2 possibilities of generating a group with 2 elements. If you're in such a way that the corresponding Cayley graph will have valency 3. So 3 involutions on one involution, one non-involution. We worked on the second case. We're looking at one involution, one non-involution. Now, if you go on, what are the possibilities here? Well, it all comes down to what is the product AX, the product of involution, non-involution, what is the order of this element? The order 2 is easy to deal with, and it has been done, but the first problem, so the first hard case to consider is when A and X give you an element of order 3. Or it could be any order if you want, but the first case to consider is when AX has order 3. And many, in fact, I believe all simple groups can be generated with an involution and a non-involution in such a way that the product has order 3. So this is what we were interested in, and this is what we were able to prove. So I'm giving you the theorem, and then I'm ending off with a picture that I think lays out the main ideas behind this theorem. What are the possibilities for, in this case? I have involution A, element X of order S in such a way that the product AX is of order 3. we were able to prove, now what are the possibilities for the group G? Because the group G is generated by an involution that, of course, it has to be of even order. This even order is either congruent to 2 modulo 4 or congruent to 0 modulo 4. We were able to show Hamiltonian cycle when it is congruent to 2 modulo 4. Now, if it is congruent to 0 modulo 4, there are 3 possibilities depending on what S is. Of what is the congruency class of S. S is either odd, either congruent to 0 modulo 4 or 2 modulo 4. So we were able to prove the existence of Hamiltonian cycle when when S is congruent to 0 modulo 4 or when S is odd, but we were unable to prove Hamiltonian cycle, only Hamiltonian path in the last case when S is just 2 modulo 4. Now, I promised a nice picture where you would sort of grasp the idea behind this. The idea is to, when you have constructed this graph, to place it on a surface of the right genus, whatever the genus, the necessary genus is, and then look at the special way this graph is embedded on this surface, and look for special configurations inside the graph that will sort of automatically give you a Hamiltonian cycle. And this example, finish off this lecture, should have you understand what lies behind. There is a graph, a nice graph. It was used for a soccer ball back in decades ago. Now we are using more complicated embeddings of graphs on surfaces on the sphere that can be embedded on the sphere. The graph is a Cayley graph of the alternating group of order 5. In fact, you can construct this graph by taking this is what you do. So the group G is A5. So even permutations, 60 even permutations of degree 5 of the group of degree 5, and I'm taking for S and defining S in such a way that X will be an element of order, an element of order 5, just 1, 2, 3, 4, 5. Okay, this permutation, and I need an evolution, but an even evolution, so it has to be 2 transpositions and 1 fixed point. So A, but I have to be careful here. What I must not, there are different evolutions that I can take, but I must not take an element in the normalizer of X. So I just have to be careful here. 1, 2, I can 5. So let's say 2, 3, and 4, 5. I hope if I'm doing this correctly. 1 goes to 1, 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes to 1, and 3 to 4, 4 to 5, 3 to 2, 2 to 3, yeah, 3 and 5. So the product is an element of order 3. So element of order 5, involution, the product is an element of order 3. So this is precisely what I had in my assumptions before. And perhaps you just believe me that this is the case. So the corresponding graph is precisely the soccer ball graph, or the so-called Buckminster-Fullerene. Fullerenes are cubic graphs for valency 4 that can be placed on a sphere and have as regions only 5 cycles or 6 cycles. This one has 12 5 cycles, and the rest are all 6 cycles. 6 cycles come from AX, because if you look at, for example, this is the identity in the group,
and say this is vertex A, vertex X inverse, and A. If I go AX, and then AX, and AXA, and so on, I will end up in a cycle of length 6, because I do AX 3 times. AX has order 3, so I will complete this in a 6 cycle. So 6 cycles there come from this permutation being of order 3, because each time I do AX, I use 2 edges. So 3 times 2, 6 edges will give me a 6 cycle. The 5 cycles come from X squared, X cubed, and so on. And this is the graph. Now the idea, and this was used in other cases as well, but in some cases it's much more complicated than in this particular case. Now think of, so you have these regions on the sphere in this particular case. I have 12 5 cycles and the rest are all 6 cycles. And the idea is to color the regions in such a way that the boundary of this region will give you a Hamiltonian cycle. So what you have to do is, if you think of these regions as points, if you want to draw a central point inside each region. Each 5 cycle has 6 cycle. Now think of it like this: central points. This transformation is called, you make the dual graph. So you take the central point in each region and you draw like this, connect the neighboring regions. Now if you are able to color the regions in such a way that there is no cycle of regions, so if you travel through all these colored regions, but in such a way that you can never come back to the same region. In other words, you have something that we call a tree of regions, or a tree of faces. If you color these faces in such a way that there is no cycle of faces, but there is a tree of these faces which has to cover all vertices. So every vertex is on one face, one colored face. And if you do that, you travel around, you get precisely a Hamiltonian cycle. So a Hamiltonian cycle in this particular graph is obtained by first coloring the regions, coloring the faces, in such a way that there is no loop of faces, and every vertex is on one colored face. Now, if you go through the boundary of this colored regions, then you get a Hamiltonian cycle. And if the two colors, green and blue, green are 6 faces of length 6, and blue are faces of length 5. And what I had before here, this is my last comment. When in the first case, when cardinality of G is congruent to 2 modulo 4, we can construct such a cycle with using just faces of length 6. When we have 0 modulo 4, we have to use one region of size S, and all other regions are of 6 cycles. When S is odd, we have to use 2 S cycles. In this particular case, S is equal to 5. So this is essentially the idea which we were able to use in order to prove existence of Hamiltonian cycles in this particular class of cubic Cayley graphs. The rest is very much open. I'm not going to talk about semi-regular automorphism maybe some other time. That problem too is still open. Thank you for being patient with me. I hope I have given you something new and something that you have at least half enjoyed, or enjoyed as much as I have. Thank you.
Thank you very much, Professor. Are there any questions?
I would like to consider a simpler definition of vertex transitivity. I say that the graph is vertex transitivity of the order n if the friend of my friend n times is my friend.
Again, friend of a friend, n times,
N times is a friend of my friend or of my friend. N times is my friend.
u0 is adjacent to u1,
Yeah.
and then what? u1 is adjacent to some...
N. No,
You
of
too?
course for n equal to 1. It's,
no,
no
but
sense.
you have
Yeah.
a sequence of
Sequence, yes. N times.
u2
Yeah.
to u3 and so on,
Yeah.
and un minus 1 is to un, and un...
And it means that UO is a friend of UN. Is it is it vertex transitive in usual sense?
But this just tells you that there is a cycle.
Right, exactly, yeah.
This would not be enough, because if you could have, I don't know, you could have like this, as I had before. You have a triangle and a
No,
four cycle.
I do not pretend that this is a general definition, but is it a particular case of the transitivity in your sense?
No, because this property is vacuously true in this graph, because it is true for this particular case, for
Okay.
this part and that part, and these two parts, they do not mix, they do not interact. So this property is vacuously true.
Exactly, yeah. Yeah, but
But this is not vertex transitive. Doesn't imply vertex transitivity.
so this kind of graph is not vertex transitive in your sense.
No, not necessarily. No, the transitivity is a property of permutation group acting on the graph, not the.
But it looks like it should be okay. At least for n is equal to 3, it is true.
Well, for n equals to 3. So, okay, give me the definition. Precise definition. Your definition, I mean, particular definition. So, the graph is with the property that if I have u0, u1, and u1 to 2,
Then
That implies
I have
U0.
U and U2.
this. This would mean that if I have a path of length 2, then I must also have a triangle. But this implies that the graph with this property, it consists of we call them cliques of complete
It's like
graphs.
your example of the first year example.
This property here
Yeah,
means that whenever I have this, I must also have that.
right.
But this implies that in the graph I have all edges. Because whenever I have this, I would also have that.
Right.
Yes. And because I have, let me see, how about this one? This one is not forced.
Obviously, there is a cycle here.
This one is not forced. This
This
one.
does not matter.
Can I?
One,
But it is
one,
not
three-
vertex transitive because this one has 3.
1, 3, 4, 2, 1. So there is a cycle.
How about 1 and
One-
4? Is 1 and 4 forced?
1, 3, 4, 2, 1.
This is forced.
Huh.
So in other words, what I'm saying is that the graph that you get is a complete, so-called complete graph. So it is true, but it is a very special example.
Sure.
Yeah. So
But The
The
question
graph with
is
this property is, yes, it is vertex transitive, but these graphs, so the graphs that you get are so-called complete graphs where every two vertices are fenced.
right.
This is the only case you get with
Only
this
case,
property.
if n is equal to 4, it is not the case.
It is, but what you get is
N is equal now not
Aha.
3 but 4.
I don't think so.
Okay. Well,
I don't think so.
what I'm trying, for me, it is not.
And then what do you do this? This is a 4 cycle, okay? It is true if you have a. It is true in this case, but do you get any other graph? I don't think so.
No,
No?
why not?
Well, unless you have a triangle, and then you get again the complete graph. So intuitively, I would say that your property or your criterion would only give me one class of graphs, the so-called complete graphs.
Yeah, but the next question is how could we describe the general property in the terms of this kind of simple properties?
Okay.
Because what I'm trying to do, why I am thinking about it, because for me, maybe you explain, it is not quite clear what is the motive to introduce this kind of property. It's just we just study symmetry or something else, because if we consider the property which I mentioned, this is something like a very famous Voyager problem. You know, the trader who should
traveling salesman.
travel
Okay.
problem. So it's something like that.
Well,
So the Hamilton cycle.
Hamiltonian cycle is precisely the traveling salesman problem.
Decision of
Yes.
yeah.
But symmetry is a different concept. So
Sure, but for me it's not clear the motive of the introduction of this
problem,
Да.
neither am I. But this was a problem that was posed, and it has, because of this problem, a lot of work has been done on the symmetry of graphs, because a lot of people were trying to work on this problem. But it is, symmetry is one concept, traversability is another concept, and there is no immediate connection.
So it's just abstract consideration.
Essentially.
No. I
lot of mathematics.
don't against.
No. Even if you were, it wouldn't really. I couldn't cancel my 30 years, even if you were against it.
Thank you very much, Professor. I'm sorry to say, but we have to finish
Yes,
because we have a meeting with the rector and we have to go. If nobody has some urgent questions to the professor, then we're completing the session. Thank you very much.